Okay, welcome back to the lecture series on group theory. So last time we just started with the subgroups, though I defined just what is a subgroup of a group and gave some examples and did not continue with some more over there. So let us start from there actually. So just recall that suppose we have G is a group and let A is subset of G, and of course A is non-empty. So we call that A is a subgroup of G if A is itself a group. So once I'm speaking about a group, of course I need a binary operation over there. So the binary operation of group of A with which it is a group is basically nothing but the binary operation star restricted at A cross A. Okay, remember that we had a binary operation star which is G cross G to G, and with respect to this binary operation G is a group. Now A cross A is subset of A of G cross G. So that means what we can do, that we can restrict this binary operation to A cross A, and with respect to this restriction your subgroup A of G, that will be a group and to its own right. Okay, and also I said that A is subset of G, so one can easily assure that A might be singleton of EG, which is just identity group, or A can be the entire group G. So if a subgroup is basically either identity or the full, these two are said to be a trivial group. And any subgroup A of G says that it is a subgroup and A is neither identity nor the full group, so these kind of subgroups are said to be proper subgroups. Remember that we told that the identity element of A is basically nothing but the identity element of G. Okay, alright. Now let us see a proposition that basically characterizes the properties of subgroup. So it says that let G be a group and H is subset of G, and of course H is non-empty. Then H is subgroup of G if and only if the following conditions satisfied. Which are those? The conditions are basically H is closed under the binary operation. Secondly, the identity element, which is basically EG, that belongs to G, we have EG inside H. So H contains the identity element of G. And number 3, if small h is in capital H, then first, so now note that small h in capital H, so small h of course should be there in capital G, and then H inverse always exists in capital G, so H inverse must be in H. So that means for every element in capital H, it contains the inverse of each element of that actually. So we can just name these properties to be closed under binary operation. We name that containing the identity, and we can name that containing the inverse. Okay, now if you look at the properties very carefully, you just see that for H be a subgroup, all these are exactly required one. So the existence of the inverse is basically given by the property 3. The existence of identity is given by property 2. And since it is closed under the binary operation, so this basically gives the associativity. So H is subgroup if and only if I need the following properties to be satisfied. Number 1, associativity, and this is basically given by property 1, because if we have H1 times star H2 star H3, so they are associated, the operation is associative in the larger group G, of course, but I just need to assure that this thing happens in H. So now since H2 star H3 this is in H, and H1 star H2 star H3 this is in H, similarly H1 star H2 this is in H, so H1 star H2 star H3 this is in H. So since the entire game is also being played inside H as well, so that's why H has associativity property with respect to the binary operation. Secondly, existence of identity element, that is directly given by property 1. Property 2. And thirdly, I need existence of each inverse, or existence of inverse of each element, and this is basically given by property 3. So we are through, right? Okay. Now there is another proposition. So to prove any subset of a group is subgroup, we just need to check these 3 properties according to this proposition. Let us call this proposition A. Now there is also another proposition, which is basically proposition B, that will make our work more easier, and that says that, so let's say H is subset of G and H is non-empty, then H is subgroup of G if and only if H is closed under the binary operation. That's a first and foremost point that a group need to satisfy, and existence of inverse. Okay, inverse of each element. Okay, so here also it is quite easy. So basically we are just focusing on condition 1, condition 1 and here condition 3. So my condition is that this property of condition 2 is basically satisfied if condition 1 and condition 3 are being satisfied. Okay, so that's quite easy. So let us consider that H is subgroup, so this will imply the properties, that is this one and this one, the properties are satisfied. Okay, because we have already a previous theorem, so maybe by previous theorem. Okay, and secondly I can do with that, let H is a subset of G satisfying the properties. Okay, so then, so first of all, H is closed under the binary operation, and second property is basically that says that existence of identity. So these two, okay, so let us keep this one, and let us write the third property that we have is basically existence of inverse. So H has inverse of each element in it. Alright, now we need to just check whether it contains the identity element of G or not. So now let small h belongs to capital be an element. So from the property that it contains the inverse of each element which are inside this subgroup or inside the set, so then of course we have H inverse, this is in H, right? Now from the closeness of the binary, the closeness of the binary operation on H, we have that H times H inverse. So now H times H inverse is nothing but the identity group element of G, right? This must belongs to in H. So that means it contains an identity element of G. So all these three properties are being satisfied. So by previous theorem again, or maybe proposition A, that is proposition A, we have that H is subgroup of G. Maybe it is not a theorem, just write it here, previous proposition, maybe proposition A. Okay. Now there is also another property or another proposition that will help us to to reduce our work. That is proposition C. Okay. So what does the proposition C says? So proposition C says that let H is subset of G, and H is subgroup of G if and only if for any small g comma small h in capital H. Yeah, of course, every time we will be considering H is non-empty. We have GH inverse is in capital H. Okay. Okay. So now first of all we need to check that it is closed under. So it takes identity of G. So let us consider H belongs to capital H. So of course H times H inverse, this must belongs to in H. That means identity element of G, this must be in H. Secondly, it takes the inverse for each element of H. So let small h is in capital H, and we have already got that it contains the identity element of G. So then EG times H inverse, which is basically H inverse, that should be there in H. And secondly and thirdly, let H1 comma H2 is in H. Now since H2 is in H, then we must have H2 inverse, this must be in H, right? So then we'll be taking H1 times H2 inverse and then again inverse of H2 inverse. Now it is basically H1 times H2, that should be there in capital H. Okay, so that means the first property, that is the identity element or presence of identity element of G, that is being satisfied. Secondly, the existence of inverse for each element of the subset, this property is being satisfied. And thirdly, the closeness under the binary operation is also being satisfied. So that's why we have that H is subgroup of G. Okay, and conversely, we have that if for all, okay, conversely, suppose if H is subgroup, then of course G of H inverse will be there in H for all G and H in capital H, right? Because if we take G comma H in capital H, then of course we have H inverse is in H. Then by closeness, we have that G H inverse in H. Okay, that's why the property is if and only if condition. In fact, here also in last properties, in property A and property B as well, proposition B A and B as well, the proofs are basically both sides. So we can prove the converse statement as well. Because if it is closed in a binary, if it is a subgroup, then of course it will be closed in a binary operation, and it will take, it will take the inverse of each element inside the subgroup. Okay, so the converse is trivial. So in fact, trivial. Okay, yeah. So now let us see that suppose, so the proposition, so suppose G is a group and H is subset of G and coordinate of H is finite. Okay, then H is subgroup if and only if H1 comma H2 is in capital H for all H1 H2 in H. That means for a finite subgroup or a finite subset, to verify whether this finite subset is a subgroup or not, it is enough to check that whether it is closed under the binary operation or not. So first of all, subgroup implies closeness is trivial, right? Now what about the converse one? So suppose for any H1 comma H2 is in capital H, we have H1 times H2 or H1 star H2 is in capital H, whatever be that. So now remember that we have already had proposition B that says that we have associativity, we have existence of the inverse, existence of identity, and we have existence of inverse, and but the proposition B says that if it is closed in a binary operation and the existence of inverse of each element, it is enough to check the subgroup property. So that's why it is enough to check here. So we have the closeness property. So it is enough to prove that for each H in capital H, we have H inverse in capital H. Okay, that is by proposition B. Okay, so first of all, see, let us consider H belongs to capital H, okay? So then H square, this must belongs to capital H. H square times H is basically H cube. This must belongs to capital H. So what is H square? It is H times H, right? Similarly, H cube times H is also in capital H, and thus it will be going on. So if we go on like this, we can say that H power n for all n belongs to natural number is in subset of H, right? Now note that this is finite, right? But we can choose infinite natural numbers, but this index set is infinite. Okay, that means this particular set, these all need to be finite. Okay, that means there exists some m belongs to natural number and n belongs to natural number such that m is not is equals n and h power m is same as h power n. Okay. Now again get back to the larger group. Now if we just see this picture in larger group G, then what we can do that h in m times h inverse is basically same as h n times h inverse, right? Then again if we just do h m times h inverse times h inverse, I'll be getting h power n times h inverse times h inverse. So that means if I just try to reduce the power, then at the left side, so that the power of the right side will be also getting reduced. But how long it will be going on? Note that we have assumed that m is lesser is not same as n. That means either we have m is strictly larger than n or m is strictly less than n. Remember, this is by will ordering principle. Okay, so then that means if m is strictly larger than n, then the right side will be getting vanished very early, or if m is less than n, then the left side will be getting vanished very early. So you can just pick without loss of generality. You can pick any one of them. Let m is strictly larger than n. Then we can easily say that hm times h inverse dot dot up to h inverse. So how long h inverse will multiply? Up to n times. But here it will be only e of g, because we already have hn times h inverse dot dot up to h inverse. So it's basically, here we have n times. Okay, so then but hn is basically nothing but h times h up to h, which is n copies of h times h inverse up to h inverse is basically n copies of h inverse. Now then this h and h inverse, by associativity property, we can club them up, so that will be getting vanished. Similarly, h times h inverse, the latter one, will be getting vanished. Thus we'll be going on and be getting exactly e of g, that is basically identity element of g, right? So then we basically have that hm times h power minus n, where h power minus n is nothing but h inverse whole power n. Okay, like n copies of h inverse is basically identity element of g, or eg. Okay, that means we have that h power m minus n is basically e of g. Now since m is strictly larger than n, that means m minus n is strictly larger than 0. So this h power m minus n, this is completely in h. That means e of g, this must be in h, right? Now what is E of G? So H of m minus n is basically same as, so is basically H times H inverse, right? So that means H of m minus n times, okay, times, we can just take here H inverse now. Note that m minus n is strictly larger than 0. That means m minus n, this is strictly larger equals 1, and of course m minus n, this must be natural numbers, right? Now we have H times H inverse is basically identity. Now what you can write it here? You can write it here m minus n minus 1 times H is basically E of G. Alright, so then we basically get that H power m minus n minus 1, this is inverse of H in capital H or in G. Alright, now since G is a group, then inverse of each element is unique. That means this must be H inverse. Okay, so that means H power m minus n minus 1, this is H inverse, and since H power m minus n minus 1 is in capital H, we must have H inverse in capital H. Alright, so then we have that H contains inverse element of, or inverse of each element in it, in the subset, or in subset which is basically nothing but H itself. Okay, so that basically turns that H is a subgroup. Alright, okay. Now we have seen several examples that we have said that suppose Z is a group, and if we take set of all even numbers, so this is a subgroup, or maybe if we take okay, so let us take, okay, I don't want to give any non-trivial example of subgroup right now. Let us stick with some more trivial, and that is let's say R plus. So the subgroup of R, one subgroup of R plus we can consider to be set of rationals, or you can consider C plus, which is basically subset of, let's say, I mean R plus is a subset of C plus, set of complex numbers. Maybe you can do an exercise. Can you think of a subset of R plus which is not a subgroup? I'm pretty sure you will be getting a lot of examples, but maybe just I make this exercise more rigorous, is that think about R minus Q. Is R minus Q a subgroup or not? Just try to check that. I'm pretty sure that you'll be able to do that. Okay. Now let us see some more strategies to create subgroups for a group. So So one of them is called something called a cyclic sub. So what is cyclic subgroup? So the definition is that let G be a group and take any element, small g belongs to capital G, be any element, then the subgroup generated by G is basically nothing but G power n such that n belongs to natural numbers. Okay? Maybe maybe we can take any integers, not natural numbers, integers. Yeah, sorry. So n belongs to all integers, where G power minus n is basically nothing but multiplying G inverse for n times. G power 0 is your identity, or maybe E of G, and G power n is multiplying for n times, and G power n is multiplying G for n times. Alright, so this is how we can define G power n and over the integers, and following these definitions and strategies you can easily check that G is a subgroup. Okay, so maybe you can take it as an exercise as well, that they're checking that is a subgroup. Okay, you just follow the properties of either a proposition A or a proposition B, whatever is fine for you, you can follow that. But of course don't take the last proposition, because remember that this proposition is only suitable for a finite subgroup. Okay, but here this subset G power n, that may not be finite because n is running over integers. Okay, so as an example, one can think of, so as we have stated last time here, that is if Z is a group, right, a group with respect to the addition as a binary operation, then the set of all even numbers. So what is the set of all even numbers? So set of all even numbers is basically 2n such that n belongs to Z, right? That means if you add 2 for n times, you will be getting 2n. For 2 times minus n, you are basically adding negative of 2 for 2 times, for n times, and we assume that, yeah, and of course when 2 power 0 means you are adding 0 numbers of 2's, which is basically trivially 0. Okay, so this is your subgroup actually. So we can just denote it as subgroup generated by 2 with respect to the binary operation addition. So that means it is basically 2 power z. Okay. So maybe you can just write that Z plus is a group, and in fact for any n belongs to natural number, the subgroup generated by n, which is basically n times d, such that d belongs to your Z. This is a cyclic subgroup generated by n. Okay, and we can call this G to be as a generator. Now let us see some operations on subgroups. Okay, so let G be a group and H1 and H2, these two are subgroups of G, right? Now if we have two subgroups of G, for how many operations we can work on these two subgroups, making sure that they will be a subgroup of G again, right? So maybe you can just consider that the class of all subgroups of G. So if you consider the class of all subgroups of G, now my question is that how many operations we can work on any two elements from this class, making sure that the product of the operation will be there in the class again. So the first choice that one can easily think of is union. If you have any two sets, you will like to have a union of them. Second, you can work on intersection. That is very basic from the set theoretic property. And the third one you can think of that product, that is specially needed for the subgroup. Okay, now we'll be defining product, what is the product of two subgroups later, but let us first go with the union and intersection. So let us check whether the union is always makes sure that union of two subgroups is again a subgroup or not. So first of all, let H1 and H2, these two are subgroups of G. So H1 is non-empty and H2 is non-empty. That means H1 union H2, this must be non-empty. Now let us consider that first of all, let us take small h1 comma small h2 belongs to h1 union h2. Maybe okay, so then h1 times h2, this has to be there in h. Okay, so if we have h1 union h2, it takes two elements, let's say h1 and h2, then h1 belongs to capital H1 and h2 belongs to capital H2. Now if we do the h1 times h2, this of course must belongs to G, but who can guarantee me that this is in either in H or in H2? Because we have chosen two different elements from different subgroups. If they are not related to the any way, then we cannot say that this entire union will be in H1 or in H2. Okay? But if we need H1 of H2 is in H1 union H2, then what we actually need? So if we need, let's say in H1 union H2, that will means that H1 times H2 should be in H1 or in H2. So if H1 times H2 is in capital H1, then what we can do, since H1 is a subgroup, I can multiply with H1 inverse on the left side and take H1 times H2, again that should be there in H1. That means I should expect that H2 must be in H1. And again, if H2 is in capital, if H1 times H2 is capital H, then of course one can expect that H1 H2 times H2 inverse, this should be in H2, which will basically imply that H1 is in H2. So that means you can see that there should be a relation between the existence of an element inside a subgroup this will be related to existence of some element inside the subgroup, and that will be implying of the existence of the same element is in another group, right? So that's why you can just modify, you can just take the help of this proposition So there's a proposition that says that basically identify or hit this particular crucial point. So it is basically that if H1 and H2, these two are subgroups of G, then H1 union H2, this is subgroup of G if and only if H1 this is in H2 or H2 is in H1. So if any one of them is embedded with inside any other, then the union will be a subgroup. So let H1 union H2, this is subgroup of G. Okay. Now if it is in subgroup of G, then what we can do, that let H1, okay, now assume that, okay, let us write that claim is that either H1 is in H2 or H2 is in H1. So let us assume that H1 is not inside H2. Okay. So then there exists some H1 belongs to capital H1 such that H1 does not belongs to H2. So my target is to prove that H2 is inside H1. So now that means, so let us take H2 is an element from capital H2. So this will imply that H1, so small h1 is in capital H1 and small h2 is in capital H2. That will basically imply that H1 times H2. Okay, so small h1 capital H1, that means that H1 belongs to H1 and H2 is in capital H2, that means H2 belongs to H1 union H2 is H2 union H1. So that means since H1 H2 is a subgroup, so this will imply that H1 H2 this is also in H1 union H2, right? Now we have that H1 H2 is in capital H1 union capital H2. Okay. Now since so H1 union H2 is in capital H1 or union H2, since it is true, then we have that either H1 H2 is in capital H1 or H1 H2 is in capital H2. So let us take the first case. So if H1 H2 is inside H1, so that will imply that if I take H1 inverse times H1 H2, this has to be in H1. So this will imply that H2 implies capital H1. Now if we have H1 H2 in capital H2, this will imply that H1 H2 times H2 inverse, this has to be in capital H2, which will imply that H1 is in capital H2. But we have already assumed that H1 is not inside capital H2. So that means this case will not be possible. Right? That means this particular case is only possible. That is H1 H2, this has to be in capital H1. Now since it is capital H1, that will basically immediately imply that H2 is in capital H1. So that means we have H2 is embedded in H1. Okay. Similarly, if we would assume that H2 is not subset of H1, then from here we could prove that H1 has to be subset of H2. Okay. So yeah, so our first case is, forward case is done. Now converse is very easy, that if H1 is subset of H2, then H1 union H2, since H2 is a larger group than H1, then it is obviously H2 again, and H2 subgroup means it is a subgroup. again we have H2 is subset of H1, and since H1 is a larger group or larger subgroup, then of course we can easily get that H1 union H2, this is basically H1, this is subgroup. Okay, so the converse is trivial. Okay, so union basically needs that either H1 subset of H2 or H2 subset of H1. Now for intersection, so what's for intersection? Let us consider that H1 comma H2, this is subset of G, or maybe this belongs to this class sigma, this class. Okay, so if we take any two subgroups from the class, then let us take H1 intersection H2. So it's of course inside H1 and this is inside H2, right? So let H1 belongs to H1 intersection H2. Since H1 intersection H belongs to, okay, maybe take any two elements. Let's say, yeah, H1 comma H2, this belongs to H1 intersection H2. That means H1 this belongs to H1 and as well as in H2, and H2 this belongs to H1 and as well as in H2. Now that means H1 and H2 both are in capital H1. So from here one can easily say that H1 times H2 inverse, this has to be in capital H1, right? Again look H1 in capital H2 and H2 in capital H2, and from here one can easily say that H1 H2 inverse is in H2 as well, right? So first you look these two elements in capital H1 and then you look these two elements in capital H2 and then take the product of H1 and inverse of H2. So that means that H1 H2 inverse, this is in H1 intersection H2, right? So this is closed under this operation. This will imply that H1 intersection H2 is subgroup. Okay, yeah. Now one can ask that what is the guarantee that H1 intersection H2 has to be non-empty? Well, H1 contains the identity element of G, and this is also contained in H2. That means H1 intersection H2, this will contain at least identity element of G. Okay, so H1 intersection H2 has to be non-empty, right? So that means intersection of any two subgroups is a subgroup, so there is no condition is needed. Now what about the product? So before working with the product, let us define formally what is the product of two subgroups. So what is the product of two subgroups? Let us consider any two subgroups H1 and H2 of G. Then we define the product of H1 H2 denoted as H1 times H2 is basically small h1 times small h2 such that H1 is in H1, capital H1, and small h2 is in capital H2. Okay, that means you take any two different elements from different subgroups and just club them up. You can do the club them up because you can find any those two elements in capital G as well. Okay, now there is a theorem that basically characterizes when the product of two subgroups is a subgroup. Alright, so the theorem says that H1 H2, this is subgroup of G if and only if H1 times H2, this has to be same as H2 times H1. Okay, note that if you take any element H1 H2 and H2 H1, these two may not be same. Why these two may not be same? Because you have not specified whether the group G is abelian or not. So if the group G is abelian, then of course it is fine. We are done. We have nothing to do. We have nothing to be worried about. But if it is not an abelian group, then we need the property that the entire product of H1 and H2 and H2 and H1 should be same as a set. Okay. It always may not be same, like H1 and any two element. If you take H1 comma H2 from H1 and H2, this may not be same as coordinate wise, but as a set wise this has to be same. That means if you take any 2 point H1 and H2, that might be same as another element called H2 prime times H1 prime. Okay. Similarly, if you take H2 prime H1 prime, that can be same as some element here, that is H1 double prime and H2 double prime. Okay, so that means H1 and H2 that be same as a set, that may not be same coordinate wise of the each element. Okay, so let us prove that. So let H1 comma H2, these two are subgroups of G, and since it is a subgroup of G, then of course we have H1 times H2 is non-empty, right? Because again you take EG from H1 and EG from H2, do the product, you will be getting EG again, and this must be in H1 H2. Okay, so it is non-empty. So assume that H1 H2 is same as H2 H1. So my claim is that H1 H2, this must be subgroup of G. So let us take A comma B, so belongs to G, such that I have chosen A from H1 and B from H2, right? Or maybe okay, so we need to prove the subgroup, right? So okay, we can choose from H1 H2 as well, there is no problem. So H1 times H2 itself. Okay, so then we can write A to B as some H1 times, let's say, K1, and B to be as H2 times K2. Okay, where H1, this belongs to capital H1 and K1 belongs to capital H2. Similarly, H2 belongs to capital H1 and K2 belongs to capital H2. Okay, so then what is your AB? Your AB is basically H1 K1 H2 K2, right? Or yeah. Okay, now what does the associativity property says? By associativity property, you can see that this particular K1 times H1, you can club these two elements, and you can find that this K1 times H1, this belongs to H2 times H1, right? So that means you can find this K1 times H1, since it is same as H1 times H2, this must be same as some H2 prime times K1 prime, where H2 prime is in H1 and K1 prime is in H2. Okay, because as I have said that H1 H2 is same to H2 H1 as a set. They may not be, the elements may not be same as a coordinate wise, but or the elements may not be same as per as per each of the coordinates, but they has to be same as a whole one, as a whole subset. Okay, so that means K1 times H2, we can write these to be as sum H2 prime times K1 prime. So just replace K1 H2 with H2 prime times K1 prime. So what will be getting? We'll be getting that is H1 times H2 prime and K1 prime times K2. So this particular one again belongs to H1, this particular one again belongs to H2. That means we have that this one is H1, this one is H2. That means we have that AB, this belongs to capital H1 times capital H2. So H1, H2, this is closed under the binary operation. Okay. Now, since it is closed under binary operation, so the first property is being satisfied. Next, what we need to check that it takes the identity element. So of course identity element is there because you may take EG belongs to H1 and EG belongs to H2. EG is basically the identity element of G. Then EG times EG is basically nothing but EG. This belongs to H1 times H2. Okay. Then so H1 times H2 takes the identity element. Okay, and then we need to check the inverse. That let we have some element, let's say maybe some C, this belongs to H1 H2. So since C is in H1 H2, we can write C to be as H1 times H2, where small h1 is in capital H1 and small h2 is in capital H2. Right? Now what is your C inverse? C inverse is basically H2 inverse times H1 inverse. Now H2 inverse times H1 inverse, this belongs to again H2 H1, and this is same as H1 H2. That means C inverse, this must belongs to H1 H2, right? So which means that H1 H2, this takes the inverse of C. Alright, that means your H1 H2, this is coming to be as a subgroup of G. Okay. Okay, so the first part of the proof is done. Now what about the converse one? So conversely, let us assume that H1 H2 is a subgroup. Since H1 H2 is a subgroup of G, so now my claim is that H1 H2, this should be same as H2 times H1. Okay, so just go with the usual procedure, that is, let's take D is in H1 and H2. So then we can write D to be as some, let's say H times K, where H is in H1 and K is in H2. Okay, now since it is a subgroup, then we have D inverse is basically K inverse times H inverse, right? So this means that D inverse, this belongs to H2 times H1. Now don't note that H1 H2, we have assumed that H1 H2 is a subgroup, right? And we have D is an element of H1 H2. That means D inverse, this must belongs to So D inverse should be there in H2 times H1. Let me just check. Did I make any mistake over here? Okay, yeah. I need to mention here that H1 H2 and H2 H1, because the product of any two subgroup can be done from both sides, right? That's what we have done here. So H1 H2 and H2 H1 both are subgroups of G if and only if H2 times H1 is same as H1 times H2. Yeah, now I think the theorem is fully satisfied. So let me just rewrite that. I'm extremely sorry for this fault. So the theorem should be H2 times H1. This is subgroup of G if and only if H1 H2 is same as H2 H1. But our proof is completely okay, because here you have assumed that H1 H2 is same as H2 H1, and considering that you have shown that H1 H2 is a subgroup. Similarly, with the same process, that choosing any element from H2 H1, so for the forward direction, choosing any element from H2 times H1, we can show that H2 H1 is subgroup of G, okay, by the same procedure. Maybe you can take it as an exercise. Just check that how much you are familiar with the process. All right, so yeah, here we need H2 times H1 also a subgroup of G. Now, since I think, yeah, now we are through. So if we have D inverse in H2 times H1, now H2 times H1, this is a subgroup, right? That means D inverse power whole inverse, this has to be there in H2 times H1, which means D is in H2 times H1. Alright. Similarly, you can assume any element D1 belongs to H2 times H1, and then we can find that D1 inverse in H1 times H2, and that will imply D1 belongs to H1 times H2. So that means we have that H1 times H2 is same as H2 times H1 as a set. So just to fill the blank, that product, when the product will satisfy, that is H1 H2, this should be same as H2 times H1 if and only if both are subgroups. Okay, so if product of any two subgroup is a subgroup, that means it has to be, subgroup from, it will commute as a set, and it should be subgroup even if we change the order or the position of H1 and H2. Okay, so these are the operations on the subgroups you can do, and that will make sure, of course you need to satisfy the conditions for each of the operations, and that will make sure that your product subgroup or the result what you are getting, that will be again a subgroup. Okay, yeah, so I think it's a good time to stop here. Maybe by the next time I'll be starting on something called cyclic group, because we have already defined a cyclic subgroup here, and as you know that a group can be a subgroup of itself. So now that's a special case, that when the group is itself generated by a particular element, so then what kind of properties there you'll be getting there. So that is also interesting. And by next time we'll be working on something called the Lagrange's theorem. That is the main motivation of studying the subgroup, and some more stuff like commutative subgroups and etc. Okay, so let's stop it here. Thank you very much.